All right, today we're going to go over free body diagrams. Okay, so free body diagrams, you've almost made them already when you were kind of dealing with net forces. But in a free body diagram, that's just simply, it's a diagram that shows all forces that act on an object. Okay, so all forces on an object. Okay. All right, so first let's break down what are the forces that are on objects, or what type of forces are possible. Okay, so when we're thinking about forces, we have two main categories. We have what we call contact forces, and we have non-contact forces. Okay, non-contact forces. And just how they sound, contact is forces that are touching something. Non-contact would be forces that there's no physical touching between the objects. Okay, which this one seems weird at first, right? But there are some forces that actually act that way. Okay, so let's go over some example of these. One of the first ones we would have is going to be friction. That's a contact force. So friction is a force that applies. Friction is a force that basically always goes opposite to motion. So it opposes motion. Okay. Then we have what we call an applied force. An applied force is just the force that you're applying to an object. So a push or a pull. Okay. We have air resistance, which is just the force due to basically air friction. Okay, so if you, for example, jump off a plane, there's a bunch of air resistance, a lot of friction from the air causing you to slow down, right? So air resistance is very similar to friction, but it's due to air, not the surface. Okay, then we have normal force, which is probably one that you haven't heard before. Okay, and last of all, we have tension. Okay, so tension is just a force in like a string or a rope. For example, if two people are like playing tug of war, the reason you get pushed is because of that tension in the rope. Okay, and normal force, which we'll go over, this is the force that acts on an object due to it being on a surface. Okay, so for example, this pen, the reason when I put this pen down, the reason it doesn't go through my desk is because the desk puts a normal force on it that holds that pen up and keeps it from going down. Okay. Then our main non-contact forces are going to be gravity, right? That causes things, that pushes things down but doesn't actually touch it, and magnetic force, right? So you've seen magnets; they can push things without actually touching them. All right. When we're doing free body diagrams, we often use the letter F to represent force, and then we use a smaller subscript to represent the type of force. For example, for friction, we would put F and then we would put a little f. For applied force, it would be again F for force and then a small a. For air, because we already used A, we just write it out. Force of air. For normal force, F of N. And you're probably already guessing what this is, F of T. Okay, so Ft, Fn. Then we have Fg, and last of all, Fm. And this letter here really just comes from the first part of whatever we're dealing with. Okay, you won't really see this one. You won't really see this, but I just wanted to bring it up. Okay, so let's work through various examples and show all the forces that exist on an object. So let's start off with a very simple example. Let's say I have, we'll work through about 5 examples, and I think that'll give you enough understanding of the type of problem you should encounter. So let's say we have a book on a table. Okay, if I'm drawing a free body diagram, I want to show all the forces on that. So I draw a simplified version of this book here. And I'm drawing the forces on the book, not the forces on the table. Okay, so we have book. I want to show the forces that exist on this. Okay, so it doesn't matter what type of object you're dealing with, if it's in space, there's always going to be gravity on it. Okay, and the arrows have to indicate the direction of the force. So gravity always pushes things down, right? Like if you throw a pencil, it's going to go down. If you jump, you go up, but then you go down. So gravity always points in the downward direction. Okay, so that's gravity. So we put F of G. I'm going to put a lowercase g for it. Okay. So again, that stands for gravity. Obviously, if I left the diagram like this would be wrong because this tells me that there's an unbalanced force and the book is going through the table. But that's not true. We know that the book is simply just sitting on the table. It's just at rest. Okay. So there has to be a force opposite to this to balance it out, because balanced forces cause no movement, right? So there is going to be an opposite force, and that's the force on the book due to the table. So the table puts a upward force, which we call the normal force. So that's just the force due to the surface of the book. So the gravity pushes it down, but the table pushes the book up, leaving it in the same spot. Okay. And it's important to keep in mind when we're doing these diagrams, whenever we have a balance, so whenever something is accelerating, means there must be an unbalanced force. If it's not accelerating, there's not an unbalanced force. So unbalanced force equals acceleration, okay? Which is, again, a change in speed or direction, so we should know that way, right? If there's no unbalanced force, then there will be no acceleration. It might stay at the same speed, but there won't be acceleration. All right, let's work through a few more examples here. So this next example that we're going to go over is going to be, let's say I have a ball, okay? This would be example 2. So a ball is pushed to the right at a constant speed. At a constant speed. Okay, so obviously, let's assume that this ball is on some type of surface, right? So we have a ball, it's on some type of surface, it's touching the surface, it's still going to have gravity, that doesn't change, F of G, and then it's still going to have a normal force, which is the force due to this surface here, pushing the ball up, right? And they're in equal amounts because they're balanced. The ball's not going through the floor. Okay, so the ball is being pushed to the right. So any push or pull, that's my applied force. Okay, applied force is just any push or pull. So it's being pushed to the right, so it has an applied force to the right. Okay, this problem though, a key word is that it is at a constant speed. In other words, it is not accelerating. So if it's not accelerating, then it must have a balanced force in the opposite direction to the applied force. Okay, but what force is that? Well, if I'm pushing the ball this way, what force goes opposite to motion? That's going to be friction. Friction always goes opposite to motion. It's the force that's opposite to motion. So this and this need to be about the same size because they're balanced. Okay, why are they balanced? Because it's a constant speed. So this is going to be F of friction. So that's the force that the floor is causing as it drags along. Okay. All right. Let's go through another example here. It's example 3. Let's say we have a car accelerating to the left. Okay, so this car is moving, and again, we don't have to draw it complicated. You can really just draw a square for most problems. Let me draw something simple here. So we'll just draw. Okay, so we have our car here. We know the car is accelerating to the, or even before that, we could always know we put gravity, right? So we put F of G, and we put F of N. That's balanced. Okay. So the car is accelerating to the left, so there must be an applied force, like the gas, right? The engine is applying a force, making it go to the left, it's pushing it. Okay, so we put an applied force to the left here. Applied force, that's what's pushing it, the engine. However, in this example, we are accelerating, so we have an unbalanced force acting on this car. So what's always opposite to motion? Well, it's going to be friction. But I can't draw it like I did this one equal. I have to draw it smaller. Okay? I have to draw it smaller because it's an unbalanced force which causes an acceleration. Okay. So those are really the more tricky ones. Let's go over some simplified ones. Let's say I have a ball falling, and sometimes problems will tell you whether they're falling with or with no air resistance. Let's say I have a ball with air resistance. Okay, so well, obviously on this ball we have gravity acting on it, right? Because gravity is always acting on everything. So we draw the object. I put force of gravity. And then as this ball falls, friction is causing is pushing it up. And this problem doesn't tell us whether or not we have a constant speed or whether it's accelerated. So depending on what it says, you put it. If it doesn't say air, if it says, you might also see problems that say neglect air resistance. That means don't worry about air resistance, and that's it. And that would be your final diagram. Okay, but I'm just going to put it in this case. Let's just make it equal. So F of air, which would be air resistance. Okay, so F of air. So again, if it's accelerating down, then this has to be bigger. If it's at a constant speed, then they would be equal to each other. But it just depends on what the problem tells you. But I wanted to keep it general to give you guys an example. But again, it can change. You have to read the problem. And if it says don't neglect air resistance, then you wouldn't even put this part up here. So it would just be like, just this part here. All right, let's do number 5. Last problem. Let's say we have a lamp hanging, right? So we have a lamp hanging, and we're showing the forces on this lamp here, on this blue. Let's make it blue. This blue object here. Well, we have gravity, obviously, right? And this lamp, it's not moving, it's not falling. So whatever force is opposite to gravity should be equal. So we know there's a force that's equal to it but opposite. So it's going to be opposite but equal. But what is that force? Well, what's holding this lamp up is the string. So what's the type of force that's in a string? It's the force of T, force of tension. Okay, remember, tension is the force that's within a rope. And that would be all, really. Okay, so I think that covers most of the problems. The main thing to look out for is whether something is at a constant speed or acceleration. Okay, so remember, when they're accelerating, one of them is going to be bigger. When they're at a constant speed, these should be the same. Okay, whether that's falling down or going to the right.